of integers. The integer represents the brightness or darkness of the image at that point. You could see that here we start from x equal to 0, 1, 2, 3, so on up to m minus 1. Similarly, for y, we could start from 0, 1, 2, so on up to n. The number of rows, that is the maximum value of x, tells us that what is the vertical resolution of the image, and the number of columns, that is 0, 1, 2 up to n minus 1, which means we will have total of n columns, tells us about the horizontal resolution of the image. Image size could be varying. It could be 256 by 256, 512 by 512, or even 1024 by 1024. And the number of gray levels tells us what is the number of bits per pixel. The term used inside the image is f of 00. This is a value. This value could be 1 bit, or it could be 8 bit, or it could be 24 bit, resulting in a binary image, a gray image, or a RGB image. When the image is shown in binary, the clarity of the image is lost. Better clarity is obtained when it is 8-bit, that is when it is gray, and still better clarity is obtained when it is 24-bit. So if we are going to consider a case where we have an image where the number of rows and columns are equal and the value of number of rows and columns is 1024, the total memory capacity required will be 1 MB. This is quite a large memory constraint on an embedded platform. So we need to consider whether such images should be considered or can we do with 512 by 512. So there is going to be a trade-off between the size of the image and the storage and the implementation level of the application. With this base in mind, we have understood that we require horizontal rows, which represents the vertical resolution, the columns, which represents the horizontal resolution, and the intensity values represent the number of bits per pixel that is required, and higher the number of bits, more storage will be required. This was also discussed when we discussed the color image or the RGB image, which required more spacing to store the image. As before, we have seen resolution is an important characteristic of an imaging system, and instead of the usual time domain system, which we say in 1D signal, here the terminology that is going to be used is spatial domain, because we are having two spaces x and y. The frequency remains the same term, but it will be again in 2D. So the term used for the frequency is same, however for time we will be representing as space. And the spatial resolution will be defined in terms of two basic parameters. The first parameter is the number of pixels, and the second parameter is the number of bits for intensity resolution. This is in other words called as bit depth. When we say the number of pixels, it tells us about the number of rows and number of columns. It could be 32 by 32, it could be 64 by 64, and as we have just seen recently, 1024 by 1024. And as a result, this number of pixels tells us something about the sampling. So what can be the effect? We could have two problems. One is we keep the number of pixels constant and we reduce the bit depth. We would get one problem. Or we keep the bit depth constant and reduce the number of pixels. If these two are happening, we will see that some problems occur in the image. The two problems that have been mentioned here are, the first problem is called as false contouring. This happens when we reduce the bit depth, which means it may happen when we use either binary image or a grayscale image, not too much, but it may happen depending upon the image size. And we are keeping the number of pixels constant, which means we are going to repeat it for 512 by 512. We are going to repeat it for, with that particular image size, we are going to reduce the bit size, and this particular thing has been implemented by us when we have considered the first MATLAB condition where we have done by considering 24-bit, which was a RGB image, 8-bit, which was a grayscale image, and a 1-bit, which was a binary image. Since we considered these three conditions, we were seeing that when we considered the binary image, it was looking like only the outline of the dog was seen. As a result, we could this results in a problem called as false contouring, which means the term contour tells us that it is the boundary, or it is this term you will see in many places of image processing. It tells us that the image, or what you call the boundary of the image, is not represented properly. The second error that is going to happen is called as checkerboard effect, or the pixelization error. As can be seen, the term pixelization tells us that it happens when we keep the bit depth constant but reduce the number of pixels. We will see an example of each of these here. We could see here, when it was 8-bit, this was okay, 7-bit also somewhat okay, but when it is 1-bit, the resolution is very, very low. This is what results in false contouring. False contouring would be better represented if we consider, as was represented, with a specific image size. That was what was considered here. The image size is same, and we have only reduced the bit depth. And when it becomes 1-bit, you could see it is very, very only the outline of the image is being treated. Similarly, when we go for 2-bit, maybe it's slightly better than 1-bit, but still many things, especially the background, etc. Here you could see some line, etc. That is almost missing. Like that, as you analyze from various bits, from 8-bit to 7-bit, maybe you don't see much of a difference, but definitely as you go to 5-bit, etc., the variation is going to be quite large, and especially when we go to 1-bit, the variation is very intense. So what do we consider as the sampling or the checkerboard effect? We said that one of the major problems with keeping the number of pixels is the memory constraint. So what we have considered is, we considered 1024 as the ideal case, but even in the implementation, usually 512 or 256 is considered. To save memory, or to consider memory as not to be a trade-off, we still reduce the size, and you could see when it is 32, it is not even clear what the picture is, and it is coming as some boxes. That is why it's called as checkerboard effect, or the pixelization error. It is appearing as boxes instead of the image. So this happens when you try to indirectly, I would say, reduce the size of the image. That is what affects the keeping the bit depth constant. That affects the clarity of the image. So hoping that the false contouring and checkerboard effect is somewhat alright, we next go on to another important concept, which is going to be the image formation. This is a gray area, which is an open research area for many people to work. The reason being, reflectance and illumination are two such quantities. If I ask you what is illumination, you would mention that it is defined as the amount of source light which will be incident on a scene element is going to be called as the illumination. However, the reflection is going to be the amount of light which is going to be reflected by the object in the scene. As a result, the reflectance is usually referred as Rxy, and the illumination is referred as Ixy. Whatever be the illumination source, usually it is a light source. Even in the camera, we see the first thing that we use is a light source. This falls on the scene element, and it passes through the imaging system. And the imaging system, as can be seen now, is a combination of rows or columns, or is a grid comprising of rows and columns, and it results in a digitized output. This particular diagram is specifically considered from Gonzalez. So the basic problem here is, how can we separate reflectance and illumination? This is a major challenge that happens in image processing. That is why many times whenever problems are considered or applications are considered, what we usually consider is that we consider that the work is carried out under normal light. We do not mention whether it is nighttime, because during nighttime the illumination may be affected, the reflectance may vary. As a result, your results are going to be results of the source image itself may be affected, which may result in the accuracy of an algorithm that has been developed by you. That is why this remains as a big challenge. I will discuss more about the reflectance and illumination separation in the forthcoming classes, but at present you have understood that when light falls on an object, the amount of light that is going to be incident, we call it as illumination. The amount of light that is reflected is the reflectance. So, is it possible for us to separate these two? Going on for the sampling, as before, we have seen it is basically related to the coordinate values. It is somewhat similar to the Nyquist frequency that we have considered in signal processing. And quantization refers to the intensity values. When we say that quantization refers to the intensity values, it tells us how many bits are present or what is the maximum intensity that we can get from a specific image. And considering the three types of images, you know that the best intensity will be got by a RGB image because it could be represented with 24 bits. We go on for a simple case to understand the concept of image sampling and quantization. Same image has been considered and a scan line has been considered, which is somewhat similar to what you do in sampling for 1D. This scan line represents the area that has to be considered beneath this. So we have got a region where Y represents the intensity values, or this may represent black, this may represent gray, slightly lighter gray, so on, and the top may represent white because you know that white has maximum intensity, black has the minimum intensity. So this may represent the intensity values, and we have tried to consider a region which is going to be continuously scanned over this particular portion. When we consider to scan a region within this particular portion, what needs to be considered is, first you will ask is, at what rate should we consider this region? For that, the solution is available in the third diagram, where you could see that the spacing is equidistant, which means this is the basic concept of sampling even in 1D, where we consider that the sampling generally is of the periodic form, where the distance between each sample is same or. So here you could see if I call this as sample 0 and this as sample 1, between this there's a small distance called as delta. The same delta is maintained between the next two and so on. So the sampling has been set to a particular value. The second stage is called as the intensity or the quantization. The intensity, as can be seen here, is represented for a gray image and not for a binary image. So the various levels could be from black to white, and here you could see actually there are 9 values because there is a limiting case in each case. So, but the colors are 8 in number, starting from black, gray, less gray, so on till we reach white. So you could see that this is 0, 1, 2, 3, 4, 5, 6 and 7, giving you 8 levels of quantization. What will happen if we reduce the quantization suddenly to 2? So what happens is what you have seen in a binary image. When it is represented by black and white, you would see that the clarity of many things are lost and they are shown either in a haphazard manner or they are sometimes not at all represented. That is why the levels of intensity is an important aspect to represent the image. When we talk about the sensor, we see that we could have different type of sensors. Sensors could be displaying the light that is incident on it, and based on the material that is used. Usually you will see silicon materials are used, and earlier charge coupled devices were being used, and now latest better materials have come up. I'm not discussing what is the material. I leave it to you to just think over what could be the latest image sensing material that will give us better clarity and better image when compared to silicon material. I think our friend Arun Raj will be able to help us more, because what has been mentioned in most of the literature is that a lot of chemical dyes are available and combinations of silicon with various materials give us better sensing capacity, and this is what is usually chosen as the sensing material. This is again the example of the continuous image, and when we are projecting this continuous image, we are getting sampling which is going to be at this rate, and intensity which is going to be, of course, more than 8 levels have been shown, but in our previous slide we have considered that 8 levels are appearing because of distinct values from black to white. They are also defined. Gray, lighter gray, so on and so forth. There are technical terms I am mentioning in a common man's language. And as can be seen, the values could be appearing as this is black, the next one is also black, the next one is also black, this is some shade of gray, that's why it's shown as 75, and I don't think it's difficult for us to identify white. If you see 255, we could call it as white. So you could see these three are white, again these three are white, these two are white, so on and so forth. And you will see slightly off-white is a value close to 255. If that's the closest number perhaps. You have even 225, this is 200, and you will see that here we have 225, which is a value slightly more white than this region. This is how the quantization effect takes place, wherein the intensity levels are changing and they are represented by various values. And we have considered a 3 by 3 image. We have considered a specific case like this, where we have simply given values as 000 or 111, which just tells us that they are the intensity values or the F values or functional values of the image. So this is how the values of the image, or what we call the intensity of the image, is represented. Technically we have said black represents 0 and the maximum value represents white. In the case of binary it was 1, but for grayscale it is 255. So this is what is observed in that particular case also. 255 for white and 0 for black. This is an example of a sampling case which has been done, and you could very well see the checkerboard effect has been created when the sampling was reduced to 16 by 16. You can try for 32 by 32 also. Sometimes in 32 by 32 you would see that the checkerboard effect is not very clear. You may have to still reduce the number of rows and columns to get the checkerboard effect. So here we are seeing what could be the minimum requirement to avoid the checkerboard effect. We have got it as 64. We have tried 32 to see whether 32 is also going to get a checkerboard effect or not. So this is just a demonstration to show that as you reduce, we said that resizing is an important component of image processing. The first step we did was take an image and resize. But because we are resizing, we should not be resizing to a very low value such that the checkerboard effect appears. This checkerboard effect is something which should be always avoided. Next question that may be asked is, can we consider 32 by 32? Because in your previous image, 32 by 32 was having a checkerboard effect. It depends upon the image. We may have to check up because the maximum size of the image in this case is only 256. Sometimes 32 by 32 may not give the expected checkerboard effect. Sometimes it may also give. It depends also on the image. Please note here the color image is retained. It has not been converted to grayscale. This is again the sampling effect when we consider the size reduction, and you could see that large number of details are lost when we reduce the size of the image. And is shown once again, which has already been discussed when we discussed why we could reduce the number of rows and columns beyond a certain stage. It is like, why can't we retain the sampling frequency below 2 FM? Similar to that, generally we do not go beyond 64. Sometimes 32 is allowed depending upon the image. Sometimes 32 results in a checkerboard effect, as can be seen here. And then what is basically sampling? Sampling is that identifying what is the actual ideal value for dx and dy so that we do not have a problem with respect to the accuracy retaining of the image, as well as we do not have problems with storage because our sampling rate is very high, means lot of space is required. We have seen that when we have a 1024 by 1024 image, 1 MB memory is required for it. So, and again, many times this image is not only stored, lot of processing is taking place, and it is also transmitted to various places. You can see images are transmitted to you, WhatsApp images, so many images you are using in your daily life also. So if the transmission is to happen, that time also the size of the image should not be too big such that transmission takes a longer time. So the basics of dx and dy is what is going to form the basics of sampling, wherein we are going to say that the distance between this and the distance between this is what is going to affect the sampling. We could see here that the distance is slightly closer. So is there going to be a loss of accuracy? So this could be represented by going in for a little bit of mathematics, wherein we would say that fxy represents the original image and fs and n represents the sample image. We are going to sample the image, that is fs of m. N is going to be obtained as f of m into delta x and n into delta y, where delta x and delta y could be got from the sampling frequency as 1 by delta x and 1 by delta y. And this forms the basics that, similar to the Nyquist criteria, if we are not going to follow this, we are likely to get the errors like checkerboard effect or the pixelization error.